Now, wait a minute. I want you to think about something peculiar. You burned a letter last week. Love letter, tax documents, whatever it was. You watched it turn to smoke and ash. Gone forever, right? The words, the ink, the paper, all destroyed. Except here's the thing that will keep you up tonight. According to the laws of physics, that letter still exists. Every single word, every curl of every letter. It's all still there, in principle. The universe hasn't forgotten a single thing about it. Sounds crazy, doesn't it? But by the end of our time together, you're going to understand exactly what I mean. You're going to see why the past isn't really gone at all. And more than that, you're going to understand something profound about the nature of time itself. Something that most people, even many scientists, never quite wrap their heads around. Let me start with something simple. Something you can see with your own eyes tonight if it's clear outside. Go look at a star. Any star. Pick one. Now, here's a question that seems almost too obvious to ask. What are you looking at? You might say, well, I'm looking at a star. Feynman, what kind of question is that? But you're not looking at a star. Not really. You're looking at the past. See, light travels fast, about 186,000 miles every second. That's quick enough to zip around the Earth 7.5 times while you snap your fingers. But space is big. Really, really big. The nearest star to our sun, a little fellow called Proxima Centauri, is so far away that its light takes 4 years to reach us. 4 years! So when you look at that star tonight, you're not seeing what it looks like now. You're seeing what it looked like 4 years ago. You're literally looking backward in time. And it gets better. You know the North Star, Polaris? Sailors have been using it to navigate for centuries. That light started traveling toward Earth about 430 years ago. When that light left Polaris, Shakespeare was writing plays. The Pilgrims hadn't landed at Plymouth Rock yet. That ancient light, carrying news from the past, is just now arriving at your eyeball. But we're just getting started. Consider Deneb, that bright star at the top of the Northern Cross. Beautiful blue-white thing. Its light has been traveling for about 1,400 years. When that light started its journey, it was around 620 A.D. The Roman Empire had fallen, the Vikings hadn't started raiding yet, and here you are, catching those ancient photons in your eye, reading a message from the past. Now think about the Pleiades, that lovely little cluster, the Seven Sisters. Their light left about 440 years ago, when Queen Elizabeth I sat on the English throne. And the Hercules cluster, that faint fuzzy patch you can barely see, its light started traveling during the last ice age, 23,000 years ago. Your ancestors were painting caves in France. The Andromeda Galaxy is even more stunning. On a clear night, away from city lights, you can see it as a faint smudge in the sky. It's the most distant thing you can see with your naked eye. The light from Andromeda has been traveling for 2.5 million years to reach your eyeball. 2.5 million years! When that light started its journey, there were no humans on Earth. Our ancestors were just figuring out how to chip stones into tools. We call them Homo habilis. They had brains about half the size of ours. And yet, that ancient light, carrying information from millions of years ago, is streaming into your eye right now. So here's the first thing I want you to understand. The past is constantly arriving. It's not gone. It's traveling toward us at the speed of light from every direction. Now think about what this means. Every direction you look, you're seeing a different time. Look at your hand, and you're seeing it as it was a billionth of a second ago. Look across the room, maybe 100 millionth of a second ago. Look at the moon, and you're seeing it from about 1.3 seconds in the past. The sun, that's 8 minutes ago. Jupiter, when it's close, about 40 minutes. Saturn, over an hour. You're swimming in the past right now. Every photon hitting your eye is a little messenger from history. Some of those messengers left home minutes ago. Some left centuries ago. Some left before the Earth existed. And they're all arriving at the same moment, right now, bringing you news from across time. Here's something strange to think about. Suppose the sun suddenly disappeared, just vanished. How long before we'd know? 8 minutes. For 8 minutes, we'd see the sun hanging there in the sky, feel its warmth, have no idea anything was wrong. Then, 8 minutes after it disappeared, the last light would reach us and the sun would blink out. And at that same moment, we'd start falling, because gravity also travels at the speed of light. The universe doesn't update instantly. It updates at the speed of light, and that means you're always, always, always looking at the past. The present is invisible. By the time light from anything reaches your eyes, that thing has already changed. The universe is a time machine, and you're riding in it, but that's just the warm-up. That's just the appetizer. Now, I want to tell you something deeper, something about the laws of physics themselves. Take Newton's laws. Beautiful laws. Simple laws. A ball rolls across the table, and Newton tells you exactly how it moves. Force equals mass times acceleration. Elegant. But here's something Newton noticed, and it bothered him a little. His equations don't care which way time goes. Let me show you what I mean. Imagine I film a billiard ball rolling across a table, bouncing off the cushion, and coming back. Now I play the film backward. What do you see? A billiard ball rolling across the table, bouncing off the cushion, and coming back. Could you tell which version was forward and which was backward? No! Both versions look perfectly natural. Both obey Newton's laws exactly. Try it with two balls. Film them colliding. One comes in from the left, hits the other. They both go off at angles. Now play it backward. Two balls come in at angles, collide, one goes off to the right. Still perfectly legal, still obeys all the laws of physics. You can't tell which way time is supposed to go. Try it with a pendulum, a weight swinging back and forth. Film it, play it backward, still a pendulum swinging back and forth. The physics works either way. This is what physicists call time reversal symmetry. The laws of motion work just as well running backward as forward. If you film any simple mechanical interaction, the movie played in reverse shows another perfectly legal event. The physics doesn't know the difference. Now let me be more precise about this, because precision matters. When I say time reversal, I don't just mean running the movie backward. I mean reversing all the velocities. If a ball was moving left, now it's moving right. If it was spinning clockwise, now it's spinning counterclockwise. You flip all the motions, and then the equations work perfectly going the other way. The technical way to say this, Newton's second law, F equals ma, involves the second derivative of position with respect to time. The second derivative, that means the equation contains t squared terms, and t squared equals negative t squared. The sign of time doesn't matter. The equation is the same whether time runs forward or backward. Now you might say, Feynman, that's silly. Of course, I can tell which way time goes. Eggs break, they don't unbreak. Coffee cools down, it doesn't heat up by itself. Perfume spreads through a room but never collects back into the bottle. A glass falls off the table and shatters. The pieces don't spontaneously jump back together. You're absolutely right, but here's the puzzle. The laws governing every single atom in that egg, every molecule in that coffee, every particle in that glass, those laws are time symmetric. They work perfectly fine in both directions. So why do eggs break but never unbreak? This is one of the deepest questions in all of physics, and we'll get to the answer. But first, I want to push deeper into what the laws of physics actually say about the past. Let me tell you about quantum mechanics now. This is where things get really interesting. In quantum mechanics, the way we describe a particle, or a system of particles, is with something called a wave function. Now, the wave function is a funny thing. It's not like a regular wave, like a wave in water. It's a mathematical object that encodes all the information about the system. Everything. Where the particle might be, how fast it might be going, which way its spin is pointing, everything you could possibly know or measure. The key equation in quantum mechanics is the Schrödinger equation. It tells you how the wave function changes over time. And here's the beautiful thing. The Schrödinger equation is also time symmetric. Not in exactly the same way as Newton's laws, but in a closely related way. If you know the wave function now, you can calculate exactly what it will be in the future, and you can calculate exactly what it was in the past. The equation works both ways. This property is called unitarity. Fancy word. What it means is simple. The evolution of the wave function preserves information. Nothing is ever lost. Nothing is ever created. The information just moves around, transforms, rearranges, but it's always there. Think of it like this. Imagine you have a code book that translates between two languages. Every word in language A corresponds to exactly one word in language B, and vice versa. Nothing is lost in translation. You can always translate back. That's what unitary evolution means for quantum mechanics. The laws of physics are a perfect translation between the state of the universe at time 1 and the state of the universe at time 2. You can always translate back. Let me try to explain this the way I might explain it to a bright 12-year-old. Imagine the universe is like a gigantic jigsaw puzzle. At every moment, all the pieces are arranged in some pattern. The laws of physics tell you exactly how to rearrange the pieces from one moment to the next. Now, the rule is, every pattern can only come from one other pattern. And every pattern can only go to one other pattern. No two different puzzles ever become the same puzzle, and no puzzle ever splits into two different puzzles. What does this mean? It means if you know what the puzzle looks like now, you can figure out exactly what it looked like before. There's only one past that leads to this present. And that past is still contained, somehow, in the arrangement of the pieces right now. The physicists call this information conservation. And let me tell you, they take it very seriously. Because if information could ever be truly destroyed, the whole mathematical framework of quantum mechanics would collapse. The equations would become inconsistent. You'd get nonsense answers, probabilities that add up to more than 100%. The universe doesn't allow that. Let me give you an example of how seriously physicists take this. For decades, there was a huge fight about black holes. A black hole is a region of space where gravity is so strong that nothing can escape, not even light. Things fall in and they don't come back out. So for a long time, people thought black holes were the ultimate information shredders. Throw a book into a black hole and it's gone forever, right? Stephen Hawking discovered something strange in the 1970s. Black holes aren't perfectly black. They slowly radiate energy. They have a temperature. They evaporate over incredibly long times, but they evaporate. A black hole the mass of the sun would take longer than the age of the universe to evaporate, but eventually it would be gone. And here's the puzzle. That radiation seemed to be random. Thermal noise, no information in it, just heat. So when the black hole finally evaporates completely, where did the information about everything that fell in go? All those books, all those stars, all those unfortunate astronauts, where did the information encoding their existence go? This bothered physicists enormously. Hawking said the information was destroyed. Other physicists, like Leonard Susskind and Gerard Hooft, said no, it can't be. If information can be destroyed, quantum mechanics falls apart. They called it the black hole information paradox, and they argued about it for 30 years. 30 years! That's how seriously they take this. After all that arguing, most physicists now believe the information does escape. It's encoded in subtle correlations in the Hawking radiation. It's scrambled beyond any hope of practical recovery, but it's there. The black hole didn't destroy the information. It just scrambled it and spit it back out over billions of years. The universe keeps its books balanced. Nothing is ever truly erased. Hawking eventually conceded the bet. He gave his opponent a baseball encyclopedia, because from an encyclopedia, he said, information can be recovered at will, just like from the universe. So let me come back to that burned letter. You watched it turn to smoke and ash. But think about what actually happened at the level of atoms. The paper was made of molecules. Long chains of carbon and hydrogen and oxygen arranged in complex structures, cellulose mostly. The ink was pigment molecules, stuck to those fibers. When you lit the match, you added energy. The molecules started vibrating violently. Chemical bonds started breaking. The paper molecules fell apart and recombined with oxygen from the air. They formed new molecules, carbon dioxide, water vapor, various other combustion products. The ash is what's left, the stuff that didn't fly away. But here's the thing. Every single atom that was in that letter still exists. Not a single one was destroyed. Not a single proton. Not a single neutron. Not a single electron. They just rearranged. They scattered into the air, settled into the ash, spread out into the environment, and the way they scattered, the exact pattern of where each atom went, that pattern is not random. It's determined by physics. It's determined by the exact initial conditions of every atom, every molecule, every photon of heat. The pattern contains all the information that was in the original letter. In principle, and I want to emphasize that, in principle, if you could track every atom that was in that letter, if you could measure exactly where each one went, if you could account for every photon of light and every vibration of every air molecule that interacted with the burning paper, you could reconstruct the letter. Not just that there was a letter, but every word, every flourish of the pen, the exact shade of the ink, everything. The information hasn't been destroyed. It's been scrambled. It's been spread out. It's been diffused into the environment, mixed with trillions of other bits of information. But it's all still there, encoded in the positions and motions of atoms. Now, can you actually do this reconstruction in practice? Of course not! You'd need to track more atoms than there are stars in the observable universe. You'd need measuring instruments of impossible precision. You'd need computers that don't exist and probably can't exist. It's utterly, completely, fantastically impractical. But that's not the point. The point is that the laws of physics don't forbid it. The information still exists. The past is still encoded in the present. It's just hidden, scrambled, but not erased. Let me give you an analogy. Imagine you have a clear glass of water. You carefully place a drop of blue ink in the center. At first, you can see the drop. It's distinct, concentrated. Then it starts to spread, diffuse. After a while, the whole glass is a uniform pale blue. The drop is gone, right? Wrong. The molecules of ink are still in there. They've just spread out. They're mixed with the water molecules. But if you could somehow tag each ink molecule, you'd find them all. They haven't disappeared. They've just become very hard to distinguish from the background. Now, the laws of physics say this. If you could somehow reverse the velocity of every single molecule in that glass, water and ink alike, at that exact instant, the ink would undiffuse. It would collect back into a drop, the movie would run backward, and it would be perfectly legal physics. The Schrödinger equation allows it. The laws of motion permit it. We never see this happen because the chances are astronomically small. To reverse all those molecules, you'd need a ridiculously specific arrangement of velocities. One particular configuration out of an unimaginably vast number of possible configurations. It's not that the laws forbid it, it's that it's unbelievably, inconceivably unlikely. But unlikely is not the same as impossible, and that distinction matters. This brings us to the heart of the matter. Why does time seem to flow in one direction? Why does the past seem gone? If the laws are symmetric, if information is never destroyed, why do eggs break but never unbreak? Why does ink diffuse but never concentrate? The answer has to do with something called entropy. Now, entropy is a tricky concept. People throw the word around and half the time they don't really know what they mean. Let me try to explain it properly. Imagine you have a box divided in half by a wall, with a gas in one half and vacuum in the other. You remove the wall. What happens? The gas expands to fill the whole box. You've seen this. It happens. But why? Here's a key insight, and it came from Ludwig Boltzmann in the 1870s. Think about it from the point of view of the gas molecules. Each molecule is bouncing around, following Newton's laws, doing its thing. It doesn't know about expanding or filling the box. It just moves. Now, there are many, many ways the molecules could be arranged in the box. They could all be in the left half. They could all be in the right half. They could be spread out evenly. They could be arranged to spell your name if you looked at them just right. Each specific arrangement of all the molecules is called a microstate. Here's the crucial point. Some collections of arrangements look the same from a big picture view, even though they're different in detail. If the gas is spread out evenly, there are gazillions of different specific arrangements that all look like evenly spread out gas. But if all the gas is crammed into one half, there are far fewer ways to achieve that. Way fewer, astronomically fewer. Let me give you some numbers. Suppose you have just 100 molecules. How many ways can they be split between two halves of a box? The most likely split is 50 to 50. There are about 100 billion ways to arrange 100 molecules, so you get 50 inches each half. But there's only one way to get all 100 inches the left half. One way versus 100 billion ways. Which do you think you'll see? Now imagine not 100 molecules, but 10 to the 23rd power. That's about how many molecules are in a breath of air. The number of ways to arrange them evenly is incomprehensibly larger than the number of ways to arrange them all in one place. The ratio is a number so big it has more digits than there are atoms in the observable universe. Entropy measures this. High entropy means there are many microstates that all look the same macroscopically. Low entropy means there are few such microstates. When you remove the wall, the gas molecules start bouncing around randomly. They're exploring the space of possible microstates, and because there are so many more microstates corresponding to spread out than to crammed in one half, the gas will almost certainly end up spread out. Not because the laws push it that way, not because there's a force driving it, but simply because there are so many more ways to be spread out than to be concentrated. It's like shuffling a deck of cards. Start with the deck perfectly sorted, hearts in order, spades in order, everything neat. Now shuffle. After a few shuffles, you have a mess. Why? Not because shuffling is biased against order. Shuffling is random. Each shuffle is as likely as any other. But there are vastly more messy arrangements than sorted ones. So you end up with a mess. Shuffle 1,000,000 times, 1,000,000,000 times, and you'll never accidentally get back to perfect order. It could happen. The laws of shuffling allow it. But you'd have to shuffle for longer than the age of the universe to have a reasonable chance. This is the second law of thermodynamics. Entropy tends to increase. Not because the laws force it, but because high entropy states are overwhelmingly more probable than low entropy states. And this is why eggs break but don't unbreak. A broken egg has higher entropy than a whole egg. There are vastly more ways to arrange molecules into broken egg than into whole egg. So once it breaks, going back is technically possible but preposterously unlikely. You'd have to wait longer than the age of the universe, much longer. But notice something crucial. The laws of physics didn't change. Time symmetry is still there. Information is still conserved. The reason for the arrow of time, the reason the past seems different from the future, isn't in the laws themselves. It's in the initial conditions. It's in the fact that the universe started in a very special low entropy state. The Big Bang, as far as we can tell, was a state of remarkably low entropy. Everything crammed together, highly ordered. Why was it that way? Honestly, we don't know. That's one of the deepest mysteries we have. But ever since the Big Bang, entropy has been increasing. Things have been spreading out, mixing up, diffusing, moving from order toward disorder. And that's why time seems to flow. That's why the past feels fixed and the future feels open. That's why we remember yesterday but not tomorrow. Now let me be careful here, because this is subtle. I'm not saying the laws of physics are different toward the future than toward the past. They're not. I'm saying that given the low entropy initial conditions, given the way the universe started, entropy is overwhelmingly likely to increase going forward, and that creates the arrow of time we experience. But here's what I want you to understand. The past isn't gone. The information from the past is still here. It's just mixed in with everything else. It's diffused, scrambled, hidden in the correlations between particles, encoded in the exact arrangements of atoms. It's all there, but we can't easily read it. Now, I want to address a common misconception directly. A lot of people think they understand this stuff, but they get it subtly wrong. The misconception goes like this. The laws of physics might be time symmetric, but obviously time really does have a direction. The past is fixed and the future is open. We can affect the future, but not the past. Surely physics must say something about that. And physics does say something about that. But what it says might surprise you. The reason the past feels fixed is that we have records of it. Memories, photographs, fossils, documents, footprints in ancient rock, light from distant stars. All of these are physical states of matter that correlate with past events. But why do we have records of the past and not the future? Is there something in the laws of physics that says so? Actually, no. The laws are symmetric. What there is entropy. When an event happens, it increases correlations. It leaves traces. The dinosaur walks through the mud. It leaves a footprint. The footprint is a correlation between the mud now and the dinosaur's foot then. As entropy increases, these correlations spread out, mix with everything else. But they're still there, encoded in the state of the universe. We have records of the past because the past was lower entropy. There's a direction defined by the entropy gradient. We call the low entropy end the past and the high entropy end the future. Our brains form memories because memory formation increases entropy. Thinking is a thermodynamic process. Computation dissipates heat. We remember the past because remembering is an entropy-increasing operation that correlates our brain states with earlier states of the world. If somehow entropy were decreasing, we would have records of the future and not the past. We would remember tomorrow and not yesterday. It sounds backwards, but physics doesn't know which direction is right. Our sense of time's direction is a thermodynamic phenomenon, not a fundamental law. Now I want to take you somewhere even stranger. I want to talk about what Einstein taught us about time. Before Einstein, people thought time was like a river, flowing steadily forward. The same for everyone. Newton imagined a universal clock ticking away, and everyone in the universe shared the same now. Midnight in New York was midnight on Mars, was midnight on a planet in the Andromeda galaxy. Einstein shattered that picture. Here's the key insight. The speed of light is the same for everyone. No matter how you're moving, no matter how fast, when you measure the speed of light, you get the same answer. About 186,000 miles per second. Always. This seems impossible. If I'm on a train moving at half the speed of light and I shine a flashlight forward, shouldn't the light go 1.5 times the speed of light relative to the ground? No. It goes at exactly the speed of light relative to the ground and exactly the speed of light relative to me. Both. For this to work, something has to give. And what gives is time. Einstein showed that time runs at different rates for observers moving relative to each other, not just appears to run at different rates. Actually runs at different rates. Your clock and my clock, if we're moving relative to each other, tick at different speeds, and both are correct. This leads to something remarkable. There is no universal now. What's happening right now on a distant star depends on how you're moving. If you're sitting still on Earth, you might say right now on that star is some particular moment. But if I'm flying past Earth at high speed, my right now on that star is a different moment. Neither of us is wrong. There's simply no fact of the matter about what's happening now at distant locations. This leads to something philosophers call the block universe, though I don't much care for the philosophical terminology. Let me just tell you what the physics says. In Einstein's picture, space and time are woven together into a single fabric called space-time. Events don't happen in space at a certain time. Events are points in space-time, period. Your birth is one point. Your death is another. The dinosaurs going extinct is another point. The heat death of the universe is another point. They're all just there in space-time, like cities on a map. From this view, the past isn't gone, because the past isn't really past in any absolute sense. The year 1900 is a region of space-time. The year 2000 is another region. They're both equally real, equally existent, as parts of the space-time fabric. Saying the past is gone is like saying New York doesn't exist when you're in Los Angeles. It exists. You're just not there. Now, I know this sounds strange. It feels like the present is special. It feels like now is the only moment that's real. But feelings aren't physics. And the physics says there's nothing special about now. Every moment is equally real. The past exists. The future exists. You're just experiencing one part of space-time at a time, like reading one page of a book at a time. Let me tell you about light cones, because this will tie everything together beautifully. Imagine a point in space-time, an event. Maybe it's you, right now, sitting there. From that point, light can travel outward in all directions. After 1 second, it forms a sphere about 186,000 miles across. After 1 year, it's a sphere, a light year across. If you draw this in a space-time diagram with time going up and space going sideways, you get a cone shape. This is your future light cone. It contains all the events you could possibly influence. Now draw the cone going backward in time. This is your past light cone. It contains all the events that could possibly have influenced you. All the events that could have sent a signal, a photon, a particle, anything that reached you by now. Your past light cone is enormous. It stretches back to the Big Bang. It contains every star whose light has reached Earth, every event in the visible universe. And all of that information, encoded in light and particles, is streaming into you right now. You are, at this very moment, being bombarded by the past. Let me give you a thought experiment. Suppose some alien civilization, very far away, has a telescope powerful enough to see individual buildings on Earth. And suppose they're 65 million light years away. What would they see if they pointed that telescope at Earth today? They'd see Earth 65 million years ago? Dinosaurs walking around? Pterodactyls flying? The asteroids streaking toward the Yucatan? They'd be watching the end of the Cretaceous period in real time. To them, it would be the present. They could make bets on what happens next. But we know what happens next. It already happened for us. Or did it? The light from those events is out there, spreading through the universe. Someone 65 million light years away, if they had good enough instruments, could watch the dinosaurs die right now. The information hasn't been destroyed. It's just traveling. And here's the flip side. Light from Earth right now is streaming outward into space. Some distant civilization in the far future might point a telescope at our location and see us, see today. To them, this moment that feels so present to you would be ancient history. The present is broadcasting itself into the future to become someone else's past. Everything is connected through light. Every event sends out messengers in all directions, and those messengers never stop. They spread forever. Getting dimmer, sure, getting mixed with noise, but never stopping. The information never disappears. So let me pull all of this together. Let me summarize why the past isn't really gone. First, light from past events is still traveling through space and reaching us right now. When you look at the stars, you're literally looking at ancient history. The Andromeda Galaxy, as it was when our ancestors were just learning to use tools. You are receiving mail from the past every second of every day. Second, the laws of physics are time-symmetric. Newton's laws, the Schrödinger equation, Maxwell's equations, they all work equally well forward and backward. Given the present, the past is completely determined, just as the future is. The equations don't know which direction is forward. Third, information is conserved. Nothing is ever truly erased. The state of the universe now contains in scrambled form all the information about every state it's ever been in. That burned letter is still there, encoded in the positions of atoms, scattered across the world but not destroyed. Fourth, in Einstein's space-time, all moments are equally real. The past is a region of space-time, just like the future. It exists, we're just not there. Time is more like a dimension of a map than like a river that flows. Fifth, the arrow of time. The feeling that the past is gone and the future is open comes from entropy, from the fact that the universe started in a special low entropy state, not from the fundamental laws, but from the initial conditions. So what does all this mean? What should you take away from this? I think it means the universe is more interconnected than it appears. It means the present is soaked in the past. Every atom in your body carries information about where it's been. Every photon reaching your eye is a message from history. The past isn't gone. It's just hard to read. Some people find this comforting. Every moment of your life is still there, encoded in the universe. Your childhood, your first love, your greatest triumphs, your worst mistakes. None of it has been erased. It's all still real, still part of the fabric of space-time. Some people find it unsettling. If the future is just as determined as the past, if it already exists as another region of space-time, what does that mean for free will? For choice? For the feeling that we're creating our lives as we go? I don't know the answer to that. That's philosophy, not physics. I can tell you what the equations say. What you do with it is your business. But I'll tell you what it means to me. It means that when you look up at the stars tonight, you're not just looking at points of light. You're looking at a time machine. You're receiving messages from epochs long gone. You're connected to a history stretching back to the beginning of time. And somewhere out there, light from this very moment is streaming outward, carrying information about you to be received by unknown eyes millions of years from now. The past isn't gone. It's just getting farther away. And the present, this moment right now, is becoming someone else's past as we speak. So treasure it, because in some deep sense, understood by the equations of physics, this moment will exist forever. Now, I want to leave you with one final thought. Tonight, if it's clear, go outside and look up. Find a star, any star. Think about the fact that you're seeing light that left years or centuries or millennia ago. Think about the information it carries. Think about how that same light has been streaming outward since that star was born and will keep going until the end of time. And then think about this. Light from Earth from this very night is streaming outward too. Someone, somewhere, somewhen might catch it, might see this moment, might wonder who was down here, looking up. Now, before we finish, let me give you one more thought experiment. This one really helped me understand what we've been talking about. Imagine a creature, a being, that exists outside of time, not living in any particular moment, but able to see all of space-time at once, like a god looking down at a map, but the map is the entire history of the universe from beginning to end. What would that creature see when it looked at you? It wouldn't see a person sitting in a chair. It would see a long, winding thread stretching through space-time. Physicists call it a world line, starting at your birth, winding through all the places and moments of your life, ending at your death. Your first step, your first word, your first kiss, your last breath, all of it would be visible at once, different parts of the same thread. To that creature, your past self wouldn't be gone. It would just be at a different point on your world line, like a city in another country, real, existing, just not where you are now. Your past isn't behind you in any deep sense. It's beside you in another direction, the direction we call earlier in time. We can't be that creature. We're stuck experiencing one moment at a time, crawling along our world lines like ants on a wire, unable to see the whole thing at once. That's what it means to be a physical being embedded in space-time rather than looking at it from outside. But physics gives us a glimpse of that larger view. It shows us that the universe is bigger than our experience of it, that time is stranger than it feels, that the past and future are more real, more present, more there, than they seem from inside the flow of moments. And I want to tell you one more thing about how this connects to something practical, something real. You know how I said light from the past is reaching us all the time? Well, scientists use this. Astronomers don't just look at the stars for fun. They use the time delay of light to study the history of the universe. When we point big telescopes at very distant galaxies, we see them as they were billions of years ago. The Hubble telescope took a picture called the Deep Field. They pointed it at an empty-looking patch of sky and left the shutter open for days. What they found was thousands of galaxies, some of them so far away that their light had been traveling for over 13 billion years. We were looking at baby galaxies, galaxies as they existed when the universe was young. That's not a metaphor. That's not poetry. That's physics. The light from those ancient galaxies carried information about what the early universe looked like. By catching that light now, we can study the past directly. We're doing archaeology with photons, and the cosmic microwave background radiation, that faint glow that fills the whole sky, that's light from even further back, from about 380,000 years after the Big Bang, when the universe first became transparent. Before that, the universe was opaque, like fog. Photons couldn't travel far without hitting something. Then it cooled, and suddenly light could stream freely. That first light, the afterglow of the Big Bang itself, has been traveling ever since. For over 13 billion years. And we can detect it, we've photographed it, we've studied its tiny variations, we're looking at the universe as a baby. The past is not just not gone. The past is visible. We're studying it right now. We're learning things about the earliest moments of existence by catching ancient messengers that have been traveling toward us since before the Earth, the Sun, or even our galaxy existed. Every time a physicist analyzes the cosmic microwave background, they're reading the universe's baby pictures. The past, written in light, preserved across billions of years, finally arriving at our instruments. That's not just beautiful. That's not just philosophically interesting. That's how we do science. The persistence of the past is what makes cosmology possible. And here's one final thought that ties everything together. We talked about how information is conserved, how the burned letter is still encoded in scattered atoms, how the diffused ink still exists, just spread out. But there's another way to think about this that I find helpful. Think about the present moment as a summary of all past moments. Everything that exists now exists because of what happened before. Every atom in your body was forged in the heart of a star that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you're breathing, all of it was made in stellar furnaces and scattered across space. You are, quite literally, made of stardust, made of the past. The shape of a mountain is a summary of millions of years of geological processes. The rings of a tree are a record of the weather, year by year. The wrinkles on your grandmother's face are a history of smiles and sorrows. Everything around you is the past, fossilized in the present. The universe doesn't have a delete button. It has a smear button. Things get spread out, mixed up, scrambled, but they don't disappear. The past becomes the present, which becomes the future. It's all one continuous process, one long movie, and every frame contains echoes of every frame that came before. That's why I say the past isn't gone, because it's not somewhere else. It's right here. It's in the structure of everything that exists. It's in the patterns of atoms, the correlations between particles, the shapes of galaxies, and the folds of your brain. The past is the foundation the present is built on, and you can't remove a foundation without the building falling down. Now, some people hear all this and they say, okay, Feynman, but what's the point? I still can't change the past. I still can't go back and fix my mistakes. What good does it do me to know the past is still there in some abstract sense? And I think that's a fair question. But here's my answer. Understanding the nature of time changes how you see yourself. It changes how you see your place in the universe. If the past is really gone, then you are just the person you are at this instant. Your history is erased, moment by moment, like footprints in the sand washed away by waves. Nothing you've done really exists anymore. But if the past persists, then you are your whole world line. Every version of you, from infant to elderly, is equally real, equally part of what you are. Your life isn't a flickering instant. It's a path through space-time, a continuous sculpture in 4 dimensions. I don't know about you, but I find that more meaningful, not less. Knowing that everything I've experienced, everything I've learned, everything I've loved is still there in the fabric of reality makes it more precious, not less. The past isn't gone, and that means everything that ever happened, everything anyone ever did, every moment of joy and sorrow and love and struggle, all of it is still real, still part of the universe, still mattering in some deep sense. That's not philosophy. That's physics. All right, I've talked long enough. Let me leave you with a summary one more time. The past isn't gone because light from past events is still traveling through space, and we see it every time we look at the night sky. The past isn't gone because the laws of physics are time-symmetric and work just as well in both directions. The past isn't gone because information is conserved, and every detail of what happened is encoded somewhere in the current state of the universe. The past isn't gone because, in Einstein's space-time, all moments exist together, and the past is just another region of the four-dimensional fabric of reality. And the arrow of time, the sense that the past is fixed and the future is open, comes not from the fundamental laws, but from the special low-entropy initial conditions of our universe. The past isn't gone. We're all connected through time. And understanding that, I think, is one of the most beautiful things physics can give us. Now go outside tonight. Look at the stars. Watch the ancient light streaming in from across time and space. And ask yourself this question. What moment from your past would you want the universe to remember forever?